Hello, I'm Gurumurthy Ramachandran, and we'll continue our discussion on uncertainties in physical measurements. In this section, we'll discuss the normal distribution. The normal distribution is also known as the Gaussian distribution. So if a measurement is subject to many small sources of random error and negligible systematic error, then the distribution of measured values is described by a symmetric bell-shaped curve that is centered on the true value of the variable. And random errors are equally likely to result in readings above and below the true value. And if we have only random errors, then after many measurements, the number of readings above and below the true value will be the same, and our distribution of results or observations will be centered around this true value. So the sampling and analytical variability in industrial hygiene and exposure assessment measurements follow this symmetric bell-shaped curve. So when I say the true value, that is obviously a philosophical construct, since it cannot be measured exactly by any means, and it's unclear whether such a thing exists. But we are going to sort of ignore these philosophical issues. However, we'll assume that every physical quantity has a true value. And for the sake of convenience, we'll define this true value of the physical variable as that value to which we approach closer and closer as more and more measurements are made with increasing care. So the true value of a measured quantity, x, is denoted by the Greek symbol mu, and the measurements of x are subject to many small random errors and negligible systematic errors, then the distribution of measurements will be a symmetric bell-shaped curve centered on the true value mu. And this mathematical function that describes this curve is called the normal distribution or the Gaussian distribution. And two parameters describe the normal distribution: its central value mu and its standard deviation sigma. And the equation at the bottom shows the equation of the normal distribution, the Gaussian distribution. So G, which has two parameters, mu and sigma, is the probability density function describing the Gaussian distribution. And so it's 1 over sigma times the square root of 2 pi, which is a constant, times e to the power minus x minus mu squared divided by 2 sigma squared. So mu is the mean, sigma is the standard deviation of this Gaussian distribution. We know that this definite integral represents the probability that a given measurement lies between two values a and b. So using the normal probability density function g, which is a function of mu and sigma, we can calculate the probability that a measurement lies within z standard deviations, that is z times sigma of the true centered value mu. And this is denoted by this equation in the middle of the page. So the probability that a measurement is within plus and minus z times sigma from mu is the integral of this g of x dx integrated between mu minus z sigma to mu plus z sigma. And this integral can be calculated easily using tables found in most books on statistics. And nowadays, actually, you can calculate it easily in Excel spreadsheets. And it is equal to the area under the curve between the two limits of integration. And in this case, it's mu minus z sigma to mu plus z sigma. So what is shown in this slide is a graph of this normal distribution, the Gaussian distribution. And on the bottom, there is a table showing different values of z and the probability of the area under the curve between mu minus z times sigma to mu plus z times sigma. So we have this bell-shaped curve with the middle point mu, which shows the peak of this distribution for g. And the area under the curve between mu minus z times sigma to mu plus z times sigma is shown in the table. And so, for instance, if we take the value of z equal to 1, we are basically saying what is the area under the curve between mu minus 1 sigma to mu plus 1 sigma. So the area under the curve within one standard deviation of the mean on either side. And we come to the next row and we say, oh, that's 68%. So what it means is of the entire area under the curve of this normal distribution, 68% lies within one standard deviation of the mean. Similarly, if we go to z equal to 2, in other words, what is the area under the curve between mu minus 2 sigma to mu plus 2 sigma? That corresponds to 95.4% of the entire area under the curve. And likewise, you can go all the way up to z equal to 4. So mu minus 4 sigma to mu plus 4 sigma contains within it 99.99% of the entire area under the curve. And so these values are very important for us to keep in mind. Some values are more useful in exposure assessment, especially in occupational exposure assessment. So given what we've learned so far, we can ask, what does the standard deviation mean? What is the interpretation of the standard deviation? So if we make a single measurement, the probability is 68% that our result will be within one standard deviation of the correct value. And this is based on our previous slide, which says that for z equal to 1, between mu minus sigma to mu plus sigma, the area under the normal curve is 68% of the entire area. So this is what we mean by uncertainty in the context of physical measurements. So if you make one measurement of x, then the uncertainty associated with this measurement is taken to be delta x, which is the uncertainty, is equal to this sigma x, or standard deviation of x. We can be 68% confident that the measurement is within one standard deviation, or in this case, the delta x of the correct value. So in the previous example, we had made 10 measurements of a gas concentration in a chamber at steady state, and the average was 20.6 parts per million. And the standard deviation was 1.505 parts per million. And so the uncertainty in any one measurement is therefore 1.505 parts per million. Now, if you make a second measurement and obtain the answer as 23 parts per million, we again can say that the uncertainty in this measurement is 1.505, and we can say with 68% confidence that the measured concentration lies in the range 23 plus or minus 1.505 parts per million. So we know the uncertainty associated with any single measurement is given by the standard deviation, sigma x. We also know that the mean, the x bar, of several measurements we have made is our best estimate of the variable of interest. So we can then say, what is the uncertainty in our estimate of the mean? What is the uncertainty in our estimate of the best estimate obtained from our n measurements? To answer this, we can again use this formula that we have encountered before. So we have our n measurements, x1, x2, up to xn, and the mean x bar is a simple function of x1, x2, up to xn. And the uncertainty in x bar is calculated using that partial differential formula that we discussed earlier. So the sigma of x bar, so this is not the sigma of x, this is the sigma uncertainty in the mean, is delta x over delta x1 times sigma x1 squared plus delta x divided by delta x2 times sigma x2 squared, and all the way up to delta x divided by delta xn times sigma xn whole squared, and then you take the square root of this whole thing. And so x1, x2, all the way up to xn are measurements of the same quantity, and each of their individual uncertainties are denoted by the standard deviation sigma x. So therefore, sigma x1 and sigma x2 and sigma xn are all equal to the standard deviation sigma x. And then we need to find the partial derivative of delta x with respect to x1, delta x with respect to x2, and so on. And each one of these partial derivatives is equal to 1 over n. And so therefore, the uncertainty in our estimate of the mean, sigma of x bar, is therefore shown by this formula, which is 1 over n times sigma x squared plus 1 over n times sigma x squared, all the way up to last one, 1 over n times sigma x squared. And so it simplifies to sigma x divided by square root of n. So what we have concluded, therefore, is that the standard deviation sigma x represents the average uncertainty in each individual measurement. So each new measurement we make will have the same uncertainty. However, the standard deviation of the mean sigma x divided by square root of n is the uncertainty in the mean, and that will slowly decrease with increasing number of measurements. So this makes intuitive sense because the more measurements we make before calculating the mean, the more reliable our answer will be. So therefore, we can improve the precision of our experiment by increasing the number of measurements we make.